I'm always fascinated by the sheer precision of it all. How we can predict decades out exactly where a planet will be.
The gravitational dance, right. It's
Now,
incredible.
that ability to forecast everything, it all comes down to celestial mechanics, doesn't it?
It does. Broadly, that's the physics of natural bodies, stars, planets, that sort of thing. But for what you're probably thinking of, like space travel,
Yeah, satellites and probes.
exactly. For that, we apply it in a more specialized field. It's called orbital mechanics or astrodynamics. That's the rule book for every mission we launch.
And the real starting point, the moment it all came together, that was Isaac Newton.
Oh, absolutely. What Newton did in 1687 was, well, it was monumental. He unified the heavens and the earth.
He showed that the thing making an apple fall is the same thing keeping planets in orbit.
Precisely. And crucially, he used his law of gravitation to mathematically derive Kepler's laws. He gave us the clean, perfect solution to the two-body problem.
Okay, so the two-body problem is that simple interaction, right? Like a binary star system. It has a neat, exact solution.
Perfectly solvable.
But if we add a third object, say the Earth, the Moon, and the Sun, what happens?
Chaos, mathematically speaking, anyway. The instant you add that third mass, the system becomes what we call non-integrable.
Meaning you can't find one clean equation to predict it all.
Exactly. The interactions are just too complex, and that's why we have to use something called perturbation theory.
So that's the workaround. You can't solve it exactly, so you kind of sneak up on the answer.
That's a great way to put it. You start with the simple, perfect Keplerian ellipse, and then you add these small calculated corrections for the gravitational tugs from that third body.
Ah, so you treat the interference as small errors you can manage instead of part of the core problem.
You got it. It's a pragmatic solution. I love the story that even Newton himself, when he was wrestling with the moon's orbit, said, "It causeth my head to ache."
Wow. So even the architect of the whole system was humbled by it. But even struggling with that problem led to breakthroughs, didn't it?
A huge one. Joseph Louis Lagrange tackled a restricted version of the problem and discovered the 5 Lagrange points.
The gravitational free parking spots in the solar system.
Yeah, you could call them that. They're these incredibly stable orbital zones, and they are absolutely critical for missions today, like the James Webb Space Telescope.
And this complexity just keeps leading to bigger ideas.
Mm-hmm.
I mean, Henri Poincaré tried to solve the full three-body problem. And what did he find?
He didn't find a solution. He found that the long-term behavior was inherently unpredictable, and that single realization, that became the foundation for modern chaos theory.
The computational power needed for all this, for navigating these chaotic trajectories in real-time space navigation, it's just staggering.
It really is.
If you're a listener trying to figure out where AI agents could make the most impact for your business, or if you need help with AI training, automation, or software development, you should check out emersilk.com.
A good point. But setting aside the computers for a second, to even start these calculations, you need to agree on a viewpoint, a stable frame of reference.
The inertial frame of reference.
Right. So think about it like this. Earth-based GPS is fine for getting around town.
But for interplanetary travel, you need a much bigger map.
A much bigger map. We shift to a heliocentric frame, a sun-centered one, and treat the whole solar system as our stable reference block.
But even that perfect reference block couldn't save Newtonian physics completely.
No.
Not near really massive body.
No, it couldn't, because of that tiny, annoying discrepancy in Mercury's orbit.
The 43 arcseconds per century.
Yeah.
That precession of its perihelion that Newton's laws just couldn't explain.
It was a total mystery for decades, until Albert Einstein published his theory of general relativity in 1916. His theory finally accounted for that missing 43 arcseconds.
So the constant striving for more accuracy is what actually pushes physics forward.
It's what always pushes it forward.
Let's just unpack that for a second. The complexity of motion itself, from Kepler's simple ellipses all the way to Poincaré's chaos, it showed us that the closer we look, the more we learn about reality. It pushed us beyond Newton and even toward discoveries like gravitational radiation.
It's an inspiring thought, isn't it? Every mathematical hurdle we face is just a doorway to a deeper physical truth. Our ability to navigate the cosmos is really a testament to humanity's relentless curiosity and progress.
Absolutely. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.